Welcome back. So I am incredibly excited today to tell you about partial differential equations. And so in this video, what I'm going to do is essentially motivate what are partial differential equations, why do we need to solve them, and I'm going to give you a lot of examples of types of PDEs that come up throughout physics and engineering and science. Okay, so this is absolutely one of my favorite topics, and I gotta say, I am just so grateful to have the opportunity to teach this to you. It's something that has, partial differential equations have changed my life. It allows you to solve problems that you can't solve without them. And so I really, really hope that this is kind of opens a door to you like it did for me. Okay, calculus is kind of the same way. It's one of those things that once you see the world through that lens, you can't unsee it. Okay, so a partial differential equation, there's a definition here. It's essentially a set of equations in terms of a multivariate function u and its partial derivatives. And so the multivariate function u that I'm going to talk about, u, is often a function of space and time. Okay, so this is my function. X is space, and t is time. And this might be a scalar function. This might be the temperature distribution on this piece of glass here. So x would be a two-dimensional x and y vector. So in general, this could be a vector, u could be a vector, and t could be time. Or you could be a scalar, this could be the temperature distribution, like I said. This could be the fluid flow vector field of the air in this room, in which case you would have three components. The x velocity u, the y velocity v, and the z velocity w. And x would be a three-dimensional space vector x, y, and z. So this is a very flexible function. It's a function of space and time, typically. And the partial differential equation is going to relate this function and its partial derivatives. So a good example would be the wave equation. So I could say the second partial derivative of u with respect to time is equal to some constant, some positive constant, times the second partial derivative of u with respect to x. So in this case, u is a scalar function. This is just a scalar function, and x is a scalar, position along the x-axis. And this would be the equation for a wave, kind of a wave u of x and t propagating at some constant velocity c. Okay, and I'm gonna, we can derive this, we can analyze this. This is just one example of what a partial differential equation looks like. So again, it is a relationship between some function u and its partial derivatives. Here I have a partial derivative in t and a partial derivative in x. Now that's different than an ordinary differential equation. So if I looked at my ODE, this is just a sidebar. If I look at an ordinary differential equation, it is usually a single derivative of a function, x of t equals some, function of x, like lambda x of t. And in this case, there is only one variable that's being varied, time. So I have an independent variable time, a dependent variable x, and I'm just taking derivatives only with respect to that independent variable time. Whereas for partial differential equations, it has multivariate dependencies. It's a function of multiple variables, x and time in this case, or maybe even multiple spatial dimensions. And so I have to think about partial derivatives with respect to each of those independent variables. Okay, good. So that is just kind of an example or a definition of what a PDE is, and this is an example. What I want to do is I want to start building up some of the most useful PDEs that we use all the time in physics and engineering and science, and then we're going to start thinking about what are some of those properties of those PDEs that are particularly useful. So maybe one of the things I'll start with is I'll just kind of describe some of the canonical PDEs. And all of these canonical PDEs that I'm going to describe have some common properties. So they are going to be linear, and I'm going to define what I mean in a minute. So they're linear, they are second order, and they are what is known as homogeneous or homogeneous, depending on homogeneous. Okay, so I'm going to define what each of these means. So linear just means that the partial differential equation can be written in terms of linear operators, where there's no nonlinear terms like u squareds or u times u sub x and things like that. Let me make a quick sidebar that oftentimes we use subscripts like u sub t to denote partial u partial t, and things like u sub x or u sub xx would equal the second partial derivative of u with respect to x squared. Okay, so oftentimes partial derivatives are denoted by subscripts, and I'm going to do the same thing here. So linear basically means that there are no nonlinear terms. There's no things like no products or cross products, no products between my various u sub x, u sub x terms. So I don't have any u squareds or u times u x's or ux times ux x's. Those would be nonlinear. And I'm going to talk actually about linear more later, so just remember that. Second order means that there's no more than no derivatives higher than second order. No derivatives higher than second order. Okay, so I could technically have a fourth derivative in x, a fourth order diffusion term. There are physical systems that have fourth order diffusion, but at least in these canonical PDEs I'm going to write down here, we're only going to think about second order PDEs. And homogeneous means that there is no time forcing or spatial forcing. So the governing rules of the system are the same throughout time, and they're the same throughout space. Now, for example, in this wave equation, this is essentially the equation for a guitar string, okay? And you could imagine building a guitar string where the first half of it is nylon and the second half of it is steel. And in that case, that will be a non-homogeneous differential equation, because the rules of the equation will change on those different halves of the guitar string, because the material properties will mean that this C is different in one part of space than in another part of space. So what homogeneous means is that there is no time-dependent forcing or spatial-dependent forcing. No time-dependent forcing or space-dependent forcing. And now that I'm thinking about it, that example I gave you is actually not a good example of an inhomogeneous equation. So I can have an equation where the constants themselves are functions of space. That's okay. But I guess here what I mean is if I actually actively force my system in time or in space, if I have some plus forcing function that's a forcing of time and space. And I'll give you lots of examples of this. For example, in the heat equation, if I have a blowtorch and I'm actively heating up a metal plate, that would be an inhomogeneous term in that equation. So we'll talk through all of this in a minute. But these are the three kind of basic properties for these canonical PDEs I'm going to write down now. And so I want to write down three basic partial differential equations. We have the wave equation, which I've actually already written down before. We have the heat equation. This is one of the most important equations in all of physics, the heat equation. And we've already seen before when we looked at potential flow, we have Laplace's equation. Laplace's equation. And Laplace's equation and heat equation are very, very closely related. So here what I'm going to do is I'm actually going to write these down, and then we're going to talk about what their properties are. We're going to confirm that they're linear, second order, homogeneous equations. So the first thing I'm going to do is I'm going to write it down in kind of a specific form for two independent variables. So the wave equation is u sub t equals a positive constant c squared u sub x. That's actually exactly what I wrote down here, just using subscript notation. And this is for a one-dimensional wave equation. I have two independent variables. I have time and one spatial coordinate x. Okay, so this is a 2D version. The heat equation is another super important equation. So this one, again, for a simple case, is u sub t, a single time derivative of u, equals another positive constant, we're going to call this alpha squared, times u sub xx. Now, these look extremely close to each other. All that has changed is that in this equation I have a single time derivative, and in this equation I have a second time derivative. But that's enough to give me completely different solutions to these two physical problems. So in the wave equation, if I take my guitar string and I pluck it, I get these standing waves. Or if I take a rope and I whip the rope, it will send this traveling wave traveling along that rope, and the shape will kind of remain constant. Whereas for the heat equation, if I have some temperature distribution in a one-dimensional piece of metal, immediately it's going to start to diffuse and average out until it all becomes a constant temperature, which is very, very, very different behavior, just because of the single additional partial derivative in this wave equation. Okay? And the third canonical PDE that we always study in physics is Laplace's equation, which is just the heat equation if I set ut equal to 0. It's the steady state heat distribution. Like let's say I have a metal plate and I heat one side in a hot bath and one side in a cold bath, and I insulate the other two sides. There will be a steady state temperature distribution that is given by Laplace's equation. So again, I'm going to write this in two dimensions as u sub xx plus u sub y equals 0. Now notice I'm actually writing this in two dimensions. This has two, so there's no time in Laplace's equation because it's for steady state heat distribution. And so this would be how the steady state heat distribution has to satisfy this for a two-dimensional heated object, for example, with boundary conditions. And again, we already saw that we already saw this from the potential flow equations also. Solutions of Laplace's equation are potentials that we can use for potential flows. Good. So these are three canonical PDEs. I also want to show you what this looks like in vector calculus notation for arbitrary dimensions, because I think we've been essentially building up partial differential equations like Laplace's equation using vector calculus, div, grad, and curl. And so I want to show you what this looks like for those cases as well. OK, good. So the wave equation in ND is going to look like u sub tt equals, again, some positive constant, now times the Laplacian of u. Okay? And this is going to be, so if u is a function of x, y, and z, this is now second partial of u with respect to x squared plus second partial of u with respect to y squared plus second partial of u with respect to z squared. And you could, in fact, write down an n-dimensional, a 10-dimensional Laplacian operator if you like. It's easy. Same thing for the heat equation. It's just u sub t equals a positive constant alpha squared, again, times the Laplacian operator of u. And Laplace's equation, aptly named, is just the Laplacian operator of u, del squared u, set equal to 0. And so these are kind of the n-dimensional. This would give you the steady state heat distribution, not just in a two-dimensional plate, but in a three-dimensional object. Then you'd take the three-dimensional Laplacian. Or an n-dimensional object. Sometimes, for example, in machine learning, you might add some kind of artificial diffusion on an n-dimensional vector, and you would need to be looking at an n-dimensional Laplace's equation. Now, there are more complicated PDEs that we use in our daily lives. Like the Navier-Stokes equations are nonlinear equations. Okay, so they don't satisfy this kind of nice property that the solutions satisfy superposition. There's other equations that are not second order. Like I mentioned that if you had u quadruple x, there are systems that have that kind of fourth order diffusion. I can have systems that are inhomogeneous. I'm forcing them in space or in time, okay, actively forcing those systems. And so we can essentially relax all of these, but these are the canonical building block partial differential equations that we use to build intuition, to understand solution techniques. And so we'll actually spend a lot of time thinking about how do you solve Laplace's equation. In fact, we can derive separation of variables, one of the most powerful techniques to solve PDEs. We can demonstrate it on Laplace's equation and then use it to solve the heat equation. You can use the Fourier transform techniques to solve the wave equation. And so these all become very, very useful as kind of building blocks to understand how partial differential equations work. Good. Are there other things I want to tell you? I'm sure there are. In fact, I think I'm going to tell you lots more in other videos. Maybe one of the things I'll mention is, what does it mean to be a linear PDE? So we've talked a lot about this for ordinary differential equations. We know that we like linear ordinary differential equations, specifically because it means that linear superposition holds. If I have two solutions of a linear differential equation, and I add up that solution, it is still a solution. And that also is what linear means for PDEs. So let me just write this out. So linear is just a way of saying that superposition holds. Superposition holds. And so what that means, let's take the wave equation, for example. If I have two solutions of the wave equation, I have two waves that are traveling at some constant speed. I've got two solutions, u1 and u2. And I add that solution up. I superimpose that solution. It will also be the solution of the wave equation because this is a linear partial differential equation. And in fact, like I mentioned, all three of these equations are linear. That is super, super useful. So Laplace's equation tells me what the gravitational potential or the electric potential is going to be in a medium away from charge densities or point masses. And again, because linear superposition holds, I can have 10 charges and just add up the fields from all of those charges to figure out what the field is going to be at some distant location x. Linear superposition is one of the most powerful tools we have in all of mathematics to handle differential equations. I'm going to say it again. When we say superposition holds, this means if u1 and u2 are solutions to PDE, then in fact any constant alpha u1 plus beta u2 also a solution. And so that allows us to essentially cook up basis solutions or eigensolutions and then take linear combinations of those for more complicated problems, for more complicated boundary conditions, geometries, et cetera, et cetera. And in fact, that's how Fourier analysis was invented. Fourier himself kind of invented this Fourier transform specifically to provide a basis of kind of eigensolutions for the heat equation. So the heat equation, you can essentially transform this into some diagonalized system using these sines and cosines, these Fourier transforms that Fourier invented. And it simplifies the heat equation, and it provides a family of unique orthogonal basis solutions so that any combination of them also satisfies the heat equation. Really, really powerful stuff. So we'll talk about all of this more, but I really, really just love this idea that linearity allows you to add up independent solutions of these equations, and there's still a solution. And linearity also relates to the operators themselves. So remember, we're talking about this is an operator. This Laplacian operator, del squared is equal to the divergence of the gradient of whatever function. So if I have the Laplacian of f, it's equal to the divergence of the gradient of f for some scalar value to f. And essentially, the gradient and the divergence operator, and therefore the Laplacian operator, are linear operators. The partial derivative of a function u is a linear operator on u. And so that's something I really want to convey to you. This is kind of an abstract concept, but very important, is that I'm just going to give you some examples of linear operators. So a linear operator on u, one example would be if I just multiply it by a constant. If I take u times 5u, that's a linear operator. And you can verify this because you can plug in u1 plus u2, and that's still equal to 5u1 plus 5u2. It's the linear operator of u1 plus the linear operator of u2. So it's linear. Another linear operator, and this is really important, and I want you to verify this. This is extremely important, is the partial derivative of u with respect to x. In fact, the partial derivative of u with respect to any of its the variables it depends on, partial u partial t, partial u partial x, second derivative of u with respect to x, the Laplacian of u, the gradient, the divergence, all of these are linear operators. And so I want you to actually verify that this L of alpha u1 plus beta u2, right? So if u1 and u2 are solutions, then I want you to plug in this and confirm that this is alpha times the operator of u1 plus beta times the operator, oops, okay, this thing is kind of a pain to erase, plus beta times the operator of u2. And I'm just going to say this again. So what linearity means is that if u1 and u2 are solutions to the PDE, then alpha u1 plus beta u2 is also a solution. And what that means for a linear operator, we build up this PDE using these linear operators. This is a linear operator on u. This is a linear operator on u. Multiplying by c squared is a linear operator on u. This is all kind of L of u equals 0. A linear operator of u equals another linear operator of u. And so to confirm that an operator, like a partial derivative, is in fact linear, we verify that if we take two functions, u1 and u2, and we add them up in some combination a plus b, then we hit that with the operator. You can essentially pop the operator out. You can pop these constants out, and you can split the sum so that it is equal to that constant a times the linear operator of u1 plus that constant beta times the linear operator of u2. And I'm going to have you get a piece of paper, actually verify this is true for partial u partial x. Verify it's true for second derivative of u with respect to x, or for the Laplacian of u with respect to a multivariate function of, let's say, x and y. Really, really, really important, okay? And these are all linear PDEs. Maybe the last thing I want to show you before, we'll talk more about PDEs a lot in the next few lectures, so I don't want to overload you here. But maybe what I will do for the last thing is just give you an example of a non-linear. So this is not going to be a canonical PDE. It's a non-linear PDE. And this non-linear PDE is going to be Burger's equation. So Burger's equation. It sounds delicious. I'm quite hungry. So this is kind of a non-linear Burger's equation. And I'm just going to write out what this PDE is, and then we'll talk about why it's nonlinear. Okay? So the partial differential equation for Burger's equation in one component is the time derivative u sub t plus ux equals some viscosity uxx. So again, this is for the one-dimensional Burger's equation. This u is just a function of time and a single spatial variable x. And it also is going to be describing how waves propagate in space and time. But because we have this nonlinear term here, this is a product. This is a product of u and ux. This is not linear. You can try to do this for ux, and this is not true. So that's another thing. I'd really like you to verify that this is nonlinear, and it's called a nonlinear convection. Okay, that's a really important term here. And we'll talk about Burger's equation and the physics more later. But I also want to point out in vector form, you can write this as a vector u sub t. This is for a higher dimensional Burger's equation, plus u dot grad of u plus equals. I have to erase twice in one video. Okay, good. This equals my Laplacian operator, my nu times Laplacian of u. And I'm going to say that this is for a vector valued u. So now u could be the velocity in the x and the y component. So this u could be u equals u in the x direction and v in the y direction. And it's a function of x and y and t. So now I have to use these kind of gradient and Laplacian operators to account for those partial derivatives. Okay, good. So let's just take a step back and do a quick summary to wrap up. So partial differential equations like ordinary differential equations, like calculus, is one of the most powerful tools we have to describe systems that change in space and time. The world around us changes in space and time. So your brain, it's changing as a function of x and t constantly. The atmosphere, the climate is changing as a function of space and time. The ocean is moving and flowing as a function of space and time. And this partial differential equation framework allows us to relate that function we care about and how it changes in space and time through these relationships of partial derivatives. Generally speaking, we want to solve for this unknown function u. We want to solve this equation for u. That's usually the goal. And that is typically easier to do for these linear PDEs, because if we can solve for kind of a basis of solutions, then linear combinations of those solutions also are solutions. But there's a lot of interesting equations, like this Burger's equation is basically kind of a 1D analog of the Navier-Stokes equations. And so, for really nonlinear fluid flows, you're not going to have that linear superposition, and we're going to have other solution techniques. Okay, a lot more on this coming soon. Stay tuned. Thank you.